Okay, so let's start the lecture today. So today we will continue talking about partially observable reinforcement learning. And this is the last lecture of this semester, so it will be slightly short. So in the last lecture, we we started talking about the mathematical models we studied partial observability, which is the partially observable Markov decision process, is the POMDP. So just a quick recap, POMDP has three main important elements, that is observation, states, and the action. So similar to MDP, we start from some initial states. The only different thing is now the states are hidden. So the learning agents no longer directly observe the states. So this part are all hidden. So the state will generate an observation at the first step. And then the learner or agent can basically make decisions based on the first observation. And the observation and underlying states will jointly decide what's the next states in the second step. And then again, the state will generate an observation by emission matrix. And then we again have the action A2 there. Okay, go on now. So we talk about major challenges in this partially observable reinforcement learning setting. Or the most important thing that makes it different from the fully observable scenario is we need to reason about the distribution of states. So this is very different from MDP, where we say the importance of states is everything about MDP and POMDP, the most important thing is we have this Markov structure. Well, the state is has a Markov transition, while the observation does not have the Markov transition. So that's why it's very important we eventually still reason about states, but different from the fully observable scenario in MDP, we can directly observe what is current states. Here we have to guess, or we have to infer, reason about what is the distribution over the states. And because of this, basically the optimal decision depends on the entire history. So that's why in the last lecture, we basically emphasized a lot. When we look at the policy, we need to look at the history-dependent policy. So the history, and the most difficult part about the action depends on history instead of current states is their exponential possibility of history. You have 2 to the omega h possibilities. So basically, in this case, we talk about in the last lecture that although we have we can write out the Bellman optimality equation using the entire history or using the belief states. But if you look at the computation, they are all exponential in the horizon, exponential in the length of POMDP. So they are all non-efficient algorithms. So we briefly mentioned in the very end of last lecture, there are a lot of existing known hardness results for POMDP. So we say for computation, that is, we talk about planning with known model. We say this is just talking about we want to find a policy, even if we already know the transition and the emission of the POMDP. So we say if we want to find the optimal policy, just the optimal history-dependent policy, it is p-space complete, which is even harder than NP-hard. And if we just want to find a subclass of the optimal policy, that is optimal memoryless policy, which memoryless policy basically only look at the policy that is no longer dependent on the entire history, but only depends on the current observation. So this clearly is not the optimal policy, but let's just discuss the best policy within this class. Even finding the best memoryless policy is NP hard. And we see the computation of POMDP is like a really, like a computation problem is really severe. Even nowadays, like there isn't any like very good solutions to tell you about like polynomial time algorithm or what is like subclass we can do polynomial algorithm. It's still like not very clear. So the second class of problem is like statistical problem. Statistical hardness. So one's perspective is like no model. No model is essentially, for example, I give you infinite number of samples, so you can estimate the model like infinite accurately based on those samples, and you just do planning. So the other end is if I have infinite computation, but I want to like learn the model, which is like the learning perspective, okay, statistical perspective. That is even with infinite computation power. So it turns out it's easy to construct some hard instance so that in the worst case, learning POMDP requires omega a to the power of h samples. So this is basically saying not only computation is difficult, even if I give you infinite computation power, that is I have like a supercomputer, then the learning is still very difficult as we need to essentially collect infinite, like exponential number of samples, which is like very, very, like you cannot really do it in practice. So today we will dig more into the statistical hardness. And we will actually see how we're gonna, like what is this a to the h counterexample is, like why in the worst case we actually require some exponential number of samples, and how could we possibly fix this problem? Or how could we, like for example, in practice, we do like study a lot of reinforcement problem or like a sequential decision making problem that waste partial observability. So why in practice we are able to address or solve some partial observable problem? So this is the topic of today. So those are like all the hardness result, which basically is very negative, saying like in the worst case for like this entire class, we cannot do too much positive things. So in order to develop some like meaningful or like which is something useful for practice, we would address this question into two sub-questions. The first question is about the problem structure. Okay. So the structure is we will ask questions, can we identify a rich subclass? This rich is very important of POMDP that is statistically tractable. So the idea is very simple, like because we already have the mathematical result saying the worst case, if we just want to learn any arbitrary POMDP, that is not possible. So the way to easily fix it is we just say possibly the hard instance in those kind of scenario are like some scenario which is not very practical, or in practice we should not hope those kind of problem is solvable. But in practice there are some other class of problem which is only a subclass of POMDP, and we as long as we solve those kind of problem related to practice, so we're good enough. So this is why we want to identify some rich subclass. Hopefully this subclass is rich enough to cover a lot of practical useful problems. And then as long as we're able to deal with that subclass, and we're in a good shape. And the second problem is about algorithm. Okay. So once we identify the subclass of problem that is statistically tractable, of course the next question is just we want to design the algorithm to learn this rich subclass. Okay. So the question we ask there is, can we design simple algorithm that efficiently learn this rich class? So today we'll talk about both perspectives, about problem structure and the algorithm. So we'll focus on the problem structure first. So in order to talk about the problem structure, like how we identify the subclass, we need to basically re-examine the hardness result. Like what is the difficult POMDP that would require a to the power of h samples? So it turns out that if we look at the original proof, these examples are not very hard to construct. It turns out it's some like POMDPs that actually with completely uninformative observations. So in the high level, uninformative essentially it doesn't really carry any information. So when we talk about the name partially observable in MDP, we kind of like somehow encoded in the message that we're saying the observation is like partially observable. So we kind of like we hope observation somehow reveals some part of the underlying states, but it turns out the hard instance is basically saying those POMDP will be hard if an observation doesn't carry any information about the states. So you can think it's like an unobserved scenario. So we'll talk about how to realize that. So basically the POMDP is that we can basically realize this uninformed observation by saying like no matter. So basically we can choose the emission. So that the observation is the same. No matter what the underlying state is. So this is like some dummy case or like a dummy observation or like a very special case of POMDP. Basically, you can think emission matrix is something like that. It doesn't matter whether I'm on a state 1, state 2, or state 3. I always will generate the same observation. Okay? And so this observation basically doesn't tell you anything about whether you're in state 1, state 2, or state 3. It's a useless observation. It's like a dummy observation. So once you have such kind of observation, then it becomes a lot easier to construct something that is very difficult to learn. So in order to construct a hardness for POMDP, we know we need to construct both emission and transition. So emission is like that. Basically, it's like a trivial emission. It is like a non-interesting emission. And then the underlying transition, we can use the previous construction, that is a combinatorial lock. Combinatorial lock, remember combinatorial lock is like a two-state MDP. That underlying we have start from some S0 states. And we first have some special action. And this will lead to, again, S0. And for whatever other actions that is in the action set, except this A1 star, that will lead to an absorbing state. And once you are in absorbing states, no matter what you do, you are staying absorbing states. Okay. And then for the correct states, every time you have a different action, only one one correct different action that will leave, make the agent remain in the correct states. Otherwise, it's always go to absorbing states. And eventually, we have S0 and S1. So basically, only if you're taking the correct action sequence, you're going to end up in this S0 state in the very last step. Otherwise, you're always going to end up in S1. And this special transition is saying, like, I will only get a reward here if reaching this final state, and everything else, we don't get any reward. And we note this combinatorial lock we previously used as a hard instance for like random exploration, but it is not hard for MDP because in MDP you can actually see what is the underlying states. You can notice like when it transitions to S1 or when it stays at S0. So basically you can use some value iteration with upper confidence bound via UCB algorithm to solve this kind of problem with polynomial samples. But what is different here? Here is we're now doing the POMDP. So in the POMDP, this is still the underlying MDP transition. But in addition to that, now we have like this trivial emission. That is, no matter what states, you generate essentially the same observation. So you have no idea which state it is. So essentially, you can think when I'm underlying running a combinatorial lock, but I have this like trivial emission, then in that sense, I have no idea what underlying state is. All my observation is when I enter the correct action sequence, I got reward 1. Anything else, I got reward 0. But I have no idea which action is wrong. So essentially, you can think this is equivalent to like entering password or something. Like you have a digital pad, like for example, you have which is like 9 actions. And no matter what you press, you don't have any observation until the very end, you know whether your password is correct or wrong. So in this case, we clearly know there's no hope we can solve this problem with polynomial samples. There's like no good way to solve this problem other than exhaustively searching all the possible action combination. That is all the action sequence, which is essentially exhausting search all the password. So in this case, it would require a to the omega h try in the worst case. Okay. So what do we learn from this hard instance? It actually, we notice a very important thing about this hard instance is like we know this POMDP actually has a completely uninformative observation. That is, essentially we can conclude that POMDPs are hard to learn. When observations are completely uninformative. Maybe we don't need completely uninformative. As long as the observations are uninformative about the two states, we can essentially embed this commutator lock into these two states, which make this POMDP difficult. So we'll talk a little bit more about how we're going to use mathematics to quantify what do we mean by uninformative and how we're going to get rid of this. So intuitively, we say observation is informative. That essentially means different states would have different observations or different distributions over observations, so that when we observe some observation, like we can essentially infer like it's higher probability in this state or higher probability in that state. Okay, so some being informative. Intuitively, we're saying like two different states should generate different distribution of over observations. So that this is essentially some minimum condition. We can say these two states are distinguishable. Otherwise, if two states just always generate the same distribution over observation, then like when you only look at the observation and without looking at the states, they look essentially the same, and you cannot really distinguish what are those two different states. Okay. So the table, essentially, we should look at the emission matrix. Remember, emission matrix is a probability of seeing observation OH given state SH at each step. Okay. So this is essentially talking about when we enter some states, what is the distribution of observation we're generating. So we can look at some simple case. Where, for example, we have two states. And two observations. So this denotes, this is like an emission matrix with only two observations and two states. And what is the uninformative like emission? Essentially, for example, when we are at state 1, we have like 0.6 probability to get first observation, 0.4 probability to get a second observation. And if at state 2, we also have essentially the same distribution, and then this just becomes uninformative. This essentially says, by looking at observation, I cannot really tell. Even with infinite number of observations, I cannot really tell whether I'm at state 1 or state 2. So what is informative? Informative essentially says we should not have the same distribution. So as long as they can be different, it's fine. So for example, it's like 0.59 0.341. As long as they differ a little bit with enough number of samples, like enough sample related to how different they are, we can essentially tell whether I'm more likely in state 1 or state 2, or with infinite number of samples, we can essentially tell with high probability I'm at state 1 or state 2, or something like that. It's more like identifiable. And this is like one of the sufficient conditions we can hope for, like basically getting rid of this type of examples, and we identify some rich subclass of problem. Okay. So it turns out we not only need to like get rid of the problem that two different distributions will generate the same distribution, we will also need to slightly strengthen this to be not only just the two different states, but also two different mixtures of states. So it turns out if you have one mixture of states and the other mixture of states generate the same distribution of observation, then you can still embed this combinatorial lock and generate the hard instance. So we need to get rid of that. We're saying for any two different mixtures of states, the observation they induce should be different. So it turns out this informative condition mathematically is equivalent to so-called, we define the new alpha weakly revealing condition. Okay, I will just say. So what I wrote here, the informative condition is equivalent to saying the OH, this emission matrix, needs to have rank S. So remember, this is in the O by S or S by O, whatever it is. Like it's a S by O matrix. So whenever we say like two mixture of states that will generate different distribution over resolution, this is essentially some like linear independent condition over this emission matrix, which this statement is equivalent to saying this emission matrix need to have rank S. And when we want to have some learning guarantees, of course, we need to have some measure of this difference. We cannot just say it's rank S, because rank S matrix can be infinitely close to rank S minus 1 matrix by just like changing some extremely small epsilon entries. So we need to have some robust version of being rank S. So we will use the alpha weakly revealing condition. Essentially, it's a robust condition of a rank S matrix. So we say POMDP is alpha weakly revealing if the S singular value of this emission matrix is greater or equal to some alpha that is strictly greater than 0. This is S singular value. So S singular value is non-zero. It's basically saying it's a rank S. Now we're not only saying it's greater than 0, but it's greater than greater equal to than some threshold. Okay. So that's why it's like a robust version of rank S. So it turns out this alpha weakly revealing POMDP is the rich subclass we will see. This is actually already defined as subclass of POMDP that is statistically tractable. Okay? So the first question to here is actually just the alpha weakly revealing POMDP. But of course, so far we haven't proved it's statistically tractable, so we will use the algorithm to say we can actually learn them in polynomial samples, so that's why it's statistically tractable. Okay. So basically now we have a candidate answer for the first question. We will essentially now design an algorithm to answer the second question and also answer the first question, answer the second part of the first question. That is statistically tractable. So this is all about the problem structure, or what is the problem structure that we identify in POMDP that is tractable. So the next part is about algorithm. So in this class, we have talked a lot about value-based algorithm like value iteration, Q-learning, a lot of basically a lot of previous algorithms we studied in MDP. For example, like a value iteration or Q-learning, or like least square value iteration, or like a GORF, or all those like fit Q iteration. They are all essentially value-based. Like the key part is learning the Q value, or like even in the multi-agent reinforcement learning setting is like learning the V value. However, we kind of like mentioned the most difficult part about learning value here is value has exponential size in POMDP. This depends on history. So whenever we want to extend a lot of like value-based algorithm, we always run into this problem that eventually depends on like when we do the function approximation, it depends on the size of value functions or like complexity of value functions. And if the value function actually has exponential size, like it depends on the entire history, and history has an exponential size. So this value also have like extremely large amount of like complexity in the value function class, which makes it very difficult to design some efficient algorithm. So what are the alternative algorithms we can possibly do in POMDP? It turns out we can possibly do another old idea, that is we do the model-based algorithm. So it seems like this model-based versus model-free thing has been talked a lot in the standard MDP scenario. But why here like it seems like a model-based, both model-based and model-free, like value-based, are like something feasible in the MDP setting. But why in the POMDP, when value-based are no longer good, why model-based are still possibly good? Because we say the value is very complex because value depends on the history. But if you look at the model size, very important thing we note is although the policy depends on the entire history, the model is just the transition and the emission. Those are the model parameters. Those has like no history in it, and those model parameters essentially has a finite number of small number of parameters. Essentially, nothing in the like number of parameters in model is like exponential. This is just the s square a size. This is the OS size. So model is actually very small. That essentially means that once we can design some algorithm that can efficiently estimate the P and O very accurately, we have a hope we can design some efficient, we can have like a near optimal policies for solving POMDP. Okay, so how are we going to design the model-based algorithm? So when we talk about learning algorithm in the previous single agent scenario, we always talk about generative model setting, exploration setting, offline setting. And here in the POMDP, the simulator setting become a little bit unclear. It's kind of like whether you observe the underlying states or you observe the underlying states. It's a little bit tricky. Like there isn't like any well-defined simulator setting. So we're directly looking at the exploration setting. Okay, it's a lot easier to identify that we just have a POMDP. We will directly interact with the POMDP as a standard learning agent will do, and we will learn the optimal policy by doing exploration at the same time. And we know when we do the exploration setting, we always will need to use some optimism. Like whether it's upper confidence bounds or it's like global optimism and something like that. So the question is what is the base algorithm? What is the base, like a model-based algorithm that we're going to use here? It turns out we will just use a very simple classical algorithm in statistics that is able to do the model-based learning. That is called maximum likelihood estimation, MLE. This is called maximum. So we just use a very simple algorithm like that. So let's first recap what is actually MLE in statistics. So MLE is a very basic algorithm in like classical statistical class. Like it's also an textbook algorithm. Basically, if you learn any like a statistical course, the first algorithm, maybe second algorithm you will learn is this MLE. So it basically says we have like a lot of distribution. Like for example, we have a Px that is a parameter by theta, or let's say we have some theta. This is my observation is x, and my model parameter is theta, and I have a lot of distribution. So for example, this can be a Gaussian distribution, where essentially I have this theta in the Gaussian distribution case is like the mean and the variance. So in this case, the theta will describe a lot of different curves of a Gaussian distribution. For example, the PDF can be looked at something like that. This is like p theta 1, this is p theta 2. And we will observe a lot of data x. So for example, x is something like here, and then we have a lot of x here. So how we should, and the problem is once we observe the data, we want to essentially estimate what is the parameter of this distribution. For example, if we already know this data come from Gaussian distribution, we want to estimate what is the mean parameter and what is the variance parameter. So MLE is a very simple principle. Essentially, it just says I will choose the parameter that maximizes the so-called likelihood. Theta is my parameter set, so that I will maximize the likelihood. Okay. So likelihood function essentially is that it will, if the true parameter is theta, what is the probability of observing this x data? I will just essentially find the parameter that maximize this. So now the question is how we're going to use this principle in designing reinforcement learning algorithm, especially combining with optimism. So it turns out once we look at the GORF algorithm, like how we're going to combine the optimism with like the physical derivation, the combination integration is in high level is kind of similar. So we talk about algorithm that is optimistic MLE. So the algorithm is, again, an iterative algorithm. It looks at a lot of episodes, episode K from 1 to capital K. And the algorithm in each episode will split into 3 steps. The first step, we'll do optimistic planning. So it's very similar to GORF. We will compute the policy and the model parameter. This is a model parameter. Essentially, in the POMDP case, this model parameter is just the P and the TNO, sorry, the transition and emission. Argmax, theta in B and pi, V pi, theta. So the only difference is, I think you recall in the GORF, we have a confidence set over the value. Here we have a confidence set over model. So we just maintain a set of models that model parameter that is in our confidence set, and then we'll later talk about how we're going to update this confidence set. And so in the optimistic planning is once we have given the confidence set, we will just find the model and the policy which will maximize the initial value. This is again the global optimism. The second step is doing the data collection. We will execute policy pi k. To collect the trajectory. Tau k equal to O1, A1, till OH, AH. And the third most important step is we will update the confidence set. After we collect the sample, update the confidence set B. So if you look at the high-level algorithm, this is essentially the same archetype of GORF algorithm we talk about in the general function approximation. And we will do optimistic planning. The only difference is now we have a confidence set over model instead of over value in the GORF. And we directly compute the best model and the policy within the confidence set. And we execute that policy to collect data, and eventually we use this data to update the confidence set. So the most important thing that makes this algorithm different from like the GORF algorithm in the general function approximation is how we design this confidence set and how we're gonna update the confidence set. And this is also where we will use the maximum likelihood estimation. So it turns out the confidence set we will use is something like the following, that we look at all the theta, and it's all the model parameter, where in the POMDP, this theta is just T and O. So we essentially look at all the collection of the model parameters which satisfy the following condition. That is summation of look at all the policy and the trajectory in my data I collected. Essentially, I look at the log likelihood. So this is a probability given by model T, that is given by some POMDP model specified by the T and O. In calculating if I'm following policy pi, what is the probability I'm going to observe some trajectory, that is tau. And so this is essentially the expansion of what we have in the likelihood here. So this confidence set essentially, so this likelihood will be greater than the maximum likelihood, theta prime in theta, summation pi tau in D, log p pi theta prime tau minus beta. Okay. So how are we going to understand this confidence set? Essentially, this is just the maximum likelihood estimation. So here we're saying with the maximum likelihood, we can also maximize the log likelihood. It doesn't matter, it's the same thing. This is essentially finding the parameter that will maximize the likelihood. This is just expand how we summation over the data. So the argmax is the MLE estimation. So MLE will give you a point estimation. So this confidence set is essentially, I will not only just include one single point, that is MLE, maximum likelihood estimation, well, I will actually include all the models so that the likelihood may not be as good as MLE, but can be slightly worse than MLE by some statistical tolerance beta. So this is very similar to in the graph, where we look at some values so that the Bellman error can be slightly greater than the smallest Bellman error plus some relaxation beta, where here, because it's maximization, so it's minus beta. So this is, again, some relaxation. And this is essentially all the algorithms. So the guarantees we can say for this algorithm is, for alpha weakly revealing POMDPs, this optimistic MLE algorithm, or MLE algorithm, will output an order epsilon optimal policy within polynomial of H, S, A, O, that is horizon, number of states, number of action, number of observation, and epsilon inverse, which is accuracy inverse, and finally the alpha inverse, which is this alpha weakly revealing parameter episodes. So the important thing is now everything is in polynomial. It's no longer something exponential in the horizon. So we have an efficient, sample efficient algorithm for learning very rich class of POMDP now. Okay. I guess this also concludes what I want to talk about partially observable reinforcement learning and essentially everything in this class this semester. Any questions? I will be happy to answer. If no questions, that will be the end of the semester. Thank you.